Now we introduce the inequality of Clausius, which is defined in this equation here, and it says that the cyclic integral of delta q over t is always less than or equal to 0. This is valid for all cycles, whether they're reversible or not. If a cycle is reversible, then it'll be equal to 0. If it's irreversible, it'll be less than 0. But what we notice is that the left-hand side of this equation represents the summation of the entropy transfer associated with heat transfer for the cycle. And you may wonder, well, why is it negative? Well, the reason that it's negative is because this statement implies that the entropy of the surroundings must increase. Because if we think about the cycle, it being a cycle, it will always return to its initial state once the cycle is completed. So the entropy within the system is not changing. And we know that the entropy of a system left to itself must only increase or stay the same. It can't decrease. And so if we take the system to be the cycle plus its surroundings, then in order for the total entropy to increase, the entropy of the surroundings would have to increase, which would be negative in terms of the heat transfer, since when we derived this equation, delta Q going into the system was positive. We can consider the inequality of Clausius to have the same importance as the Kelvin-Planck and Clausius statements of the second law. So with this expression, we're now in a place where we can actually form expressions for the second law, and also we can use the inequality of Clausius as a reality check when we're carrying out analyses to make sure that it's satisfied.